Let you drive.
Real. Yeah. Sounds good. Actually, I've got some updates for you. Okay.
Can you guys see my screen?
Yep.
Okay. So thanks for joining, guys. The goal of this is to go through the PR that will bring the accelerated tree mesh to SimPEG. There were just very few minor changes to regularization and a few of the existing examples. Did you say something, Lindsay?
Yeah, Joe joined us.
Ah, perfect. The man. Hi, Joe.
Hey.
That's good that you're there because you're the main audience. Not that all of you are not important, but Joe is really important. Okay, so I'm not going to go through the changes because they're not super exciting. What I am bringing in though is are two functions to deal with the meshes. Sorry, I'm just going to find it in the PR here. It is currently in model utils. I believe, Joe, you're proposing to move them to discretize, which is not a bad idea.
The other quick one, Dom, that I saw, I took a very brief look at this yesterday.
Yeah.
I think that, because you have some coordinate rotation stuff in there too?
No, I don't. Oh, you mean elsewhere? Yeah, probably.
Yeah, spherical to Cartesian and vice versa. I think we can think about moving that to discretize as well. I've got some stuff in there already for getting in between cylindrical meshes and Cartesian meshes.
Okay.
So I think that might be suitable, but we don't necessarily actually need to do that like right away. I think there's no problem bringing it in on SimPEG and then pulling it out later too.
Okay, sounds good. Sorry, I was trying to go there, but now I'm lost again. Yeah. So okay. So the first function, I'll go through a notebook after because it is going to be the example for the octree. This guy here. But let's just look at the functions, or maybe let's start with a notebook then. Yeah. All the notebook is doing, which will be the example, is to create a Gaussian topography, to put some points, some survey on top of it, and then create a mesh. And those are the two functions that I'm proposing that I would love that you guys try them and improve them if possible. Craig has been working with those, but there's immediately space for improvement. So the first one is to build a mesh centered over a cloud of points, right? So we often want to just give how far we want to pad out, what's the smallest cell octree level, and then sort of like to locate it, to position it right away over topography or points.
Yeah.
That
mesh builder is general for like, can I put the tensor there? Is that kind of a function?
Yeah, you can put a tensor. 1 sec, I will bring it up. Yeah, so this part is for tensor.
Okay.
And the other part is for tree mesh.
Right. So H is an array, like a size of 3, right? 1D array, size of 3.
That's right.
And that's actually same for both tree and the tensor mesh. Is that correct?
That's correct. Yeah.
Okay, I see.
And then currently, what I've done is that you see this pad this variable. This just tells you how far you want to go outside of the box of XYZ. So you send it XYZ locations. It will center it on that box.
Okay.
And it will pad out in the I guess 6 other dimensions with this guy here.
And Dom, XYZ is just like a cloud of points. It doesn't have to actually be a specific surface. Like if I give you a 3D volume, that would also be okay?
That's right.
Cool.
It's XYZ. Yeah, so it's just going to find the max min in all the dimensions and center it over it.
Right. And then pad dist, is that a scalar or like a...
It's a 2x3 matrix. I tried to put it there. So it's the distance on in the west, east, south, north, down, up.
Okay. Good.
And then you have two options. You can center the mesh in the middle. Like let's say you want padding vertical up, then you just center in the middle, or center. It's top or center. I'll show you the example with center. So for instance, here I'm telling it like center it on topography and put it in the center of the mesh. And I gave it some distances. Okay. The second function is to refine, because now we changed a little bit how we were breaking it down, how Joe implemented it, and he gave us the switch to finish the mesh. Basically, Joe, can you give a brief explanation again what the finalize does? It basically constructs it, right?
So as it's building the mesh, it's dividing everything. It basically doesn't as it's building the mesh incrementally, it initializes nodes and cells. But after it's done, then it will go through and determine everything else. So it'll build all the faces, edges, and find all the hanging things. So you have to, but it only does that once.
Yeah, it only does that.
So that once you're done building it.
Yeah, that's right. So that means, okay, for instance, here, I want to break down the mesh. I'll go through the refine tree function later, but I want to discretize coarser on the topography because the topography is pretty large, right? So I'm only going to discretize on the second and third tree level, but I don't want it to construct it now, so I'll hold down the construction of the mesh by inserting a false statement, and then I'm going to call that function again with my survey locations. And I'm going to discretize finally at the highest level on this one. So I'm going to ask for 2 cells around my OBS locations, and then this coarser for topography.
One more quick question for Joe here. So is finalizing method on the mesh? So if in line 45, if Dom had said finalize equals false, and then we did mesh.finalize after that, is that reasonable?
I think I had something in there to do that. I think there's a finalize function on the mesh.
Okay.
Yeah. So you see, I'm just using I'm just using that function here. If finalize is true, then it's calling mesh.finalize.
Okay. Cool.
Yeah.
So Dom, can you repeat the first comment for like at line 42? NCPED 053. What does it mean?
Okay, I'll put it side by side here. So this is the function, refine tree.
Okay.
And this is, I'm calling it here, right? So there are three ways that I think we want to break down the mesh. Right now, I have implemented just the point and the surfaces, but I think we probably want to have a box, some sort of a box option.
Yeah.
So right now it's points. I'll give you an example later, but basically points will create a cloud of points around the points that you're defining in two-dimensional space to be able to break down to the highest level, second, and third. The 5 here means that I'm asking for 5 points at the second level around the topography. Oh, sorry. If it was a point here, it's a surface. It's different, but around a point.
So that could be like a list of basically any length, but here you're just choosing to work with 3 levels of refinement. Is that true?
Yeah, that's right. We could generalize this and keep increasing this. We just need to add checks that the list cannot be longer than the number of actual levels, basically. Yeah, we could do that. Yeah, that's right. Here right now, I'm just forcing only the to be the 1, 2nd, and 3rd level.
Okay.
Okay.
And what's the reason, like using 0 there, like for the first one?
Okay, let me show you that measure. So I'm just gonna run it, and it's super fast, right? Because thanks, Joe, it's amazing. So I'm just gonna show you that mesh.
Mm-hmm.
1 second. Oh, hold on, that will crash for sure. Yeah. Okay. So here the idea is that so topography is just a Gaussian. I haven't put it here, but it's just a Gaussian. And the idea is that often topography extends far out, and we don't want a highest discretization on topography. Like we might just want to have something coarse enough.
Oh, I see.
So I'm giving 0 for the highest structure level. So you see that once we're out of the observation points, maybe I'll put the data if I have them. Yeah. So my observation points are here.
Okay.
I'm only going to do the highest structure level near my points, but topography, I'm just going to coarsen at the second and third level. It's just an option. It's an option to be cheaper.
I think, yeah, okay, yeah. Okay, so that's a strategy. I see. Gotcha.
If I do this.
Yeah.
Hold on.
Okay, probably do.
It should have worked. Oh yeah, it was still running. So now you see that the highest structure level is everywhere near topography.
I see.
I only ask for 1 point, so if you're too close, right, sometimes you're not going to catch it. So let's just add another. Let's just add another point.
Oh, I see.
So now it's nice 2-level everywhere.
So sorry, what happened if you get rid of line 45?
Yeah, so it's not gonna be okay. Yeah, that's a good point. So here you see the only thing that line 5 does is ask for 2 discretization over the points.
Right.
And since topography and the points are so close, it's probably not going to change anything. So I'll do this, but then I'll finalize here.
Oh yeah, can you set that NCPEG to 0, not 2?
This guy here, yeah. So now it's just second and third level.
Gotcha. So I think here in any kind of UBC code, that's like a prox topo function. Is that right? Like yeah, you're not really discretizing the topography really well, like just kind of but poorly.
Yeah, I'm not sure what prox. I think prox topo. Yeah, I think you're right. I think you might be right. Yeah, it just coarsen faster, right?
It's only like a use probably like a second step, and not sure what second level or something like that, and then just discretize the source location.
Yeah,
Yeah,
I'm not too sure.
Good, nice.
So I think we would want a box option so that we can define just like a lower and upper corner and then discretize at different levels inside, right?
Right.
If you guys want to do that.
Yeah.
I mean, I wanted to
just the points. Is that the like? Can you use just the points?
Yeah. So I just briefly prepared for it. So I'll recreate the mesh here. And I'm just going to insert 1 point. Okay, it has to be a column format, so I'm just creating a vector of 1 by 3. And I find out that it's broken. I can only put right now 1s or 0s. It doesn't increment, so I'll need to fix it to loop over. But okay, let's start with 1 point. I'm not going to put this in because, okay, so let me just, and I temporarily just put the line in the function to, where is this? Yeah, I just temporarily added this line so that it outputs the location of the points. I just hacked it.
Local.
Yeah. Okay, I'm just gonna put that point in. Did I? Oh yeah, I put 1. Okay, that's what I was wondering. Sorry. So I have 1 point. This one in the center here is minus 2.5, 2.5. right? And then it just created a grid of one tree level all around, as close as it could.
Okay.
If I rerun it with, let's say, let's try this. I haven't tried that. And load the point. Right, so it did one level, and then that's the third level around it.
Dom, quick question for you. It looks like sort of in the bottom left corner. Yeah, right where your mouse is. What happened there? Because it looks like we haven't actually, the tree isn't balanced.
Yeah, Joe. I don't know.
Joe, you're muted.
Yeah. So where your mouse is?
Yeah, here.
Why doesn't it not look balanced there?
Like it didn't. I guess it didn't do the same thing as this one here, right?
Oh no, it is actually.
Is it just
Sorry, Dom.
It
looks like it looked to me. There we go. Oh wait.
No,
No, I think it's okay because it looked to me, Dom, that if you go, just move your mouse to the right a little bit. I sort of thought that
Here.
and up. It looks to me from just the view here that was a 1 level.
No, that's a 2 here.
So it is actually, that is okay. Okay.
But I don't understand sometimes why, for instance, it didn't break that one here at a level 2, right? Why is it at level 3 right away? I'm not sure.
Yeah, that's.
I mean, it doesn't look like you're putting any points in there, but I don't know why.
But these guys don't have points either. Like this cell doesn't have a point in it either, right? Sorry, it's hard to see, right? But this guy doesn't have any point in it, and it did
right,
the
but
transition.
that one was broken by the one next to it.
So if I have a point here, then it would do it.
So if you moved over move to the right 2 sections, one more. So if that one had been broken up again, the one to the left would have been broken down, but it was never broken.
Okay. Okay. Why is this one? Okay, you see this cell, that's a level 1, right?
Yep.
Or like the highest level. And then this one is broken.
So that's level 2 right there.
Yeah, that's level 2.
Right? That makes sense. I mean, it was.
Why is not happening here?
Because none of its neighbor cells were level 1.
Yeah, like a diagonal one isn't its direct neighbor, sort of. If you look at the top left one of the central cluster of points, then if you go up one and to the side one, it's going to break that down.
Yeah.
You go to the bottom left point in the center cluster of points, it breaks the one down to the left and the one to the bottom, but it's not breaking the diagonal. Does that make sense?
No.
So Dom, let me try and summarize what Devin just said.
Yeah.
That makes sense. So if you look at the cell that your mouse is in right now, that whole cell needed to be refined 1 level because its immediate neighbor had a level 1 refinement, right? So if you go down 1 cell and over.
Yes. Okay, I got you.
Right, that's level 1, and so then you have to refine that whole.
Yeah, that makes sense. Okay. So maybe we need to play around a little bit with how we create those this cloud of point to assure that there is no hole, right? Because right now I'm kind of you see this kind of an empty row. Or maybe I guess because if I do this, probably gonna be nicer, right?
So, is there any sort of reason you don't want to do it as like a refined function instead of just inserting a bunch of points?
Yeah, you'll have to teach me how, man. But it's just the thing is that the functions are maybe less intuitive to play around with. But yeah, I'm open. But
so if you just give it a single point, right? You just like that for this example, you just give it a single point and measure the distance from that point and refine based off of the distance.
But based on what though? Because we don't get centers, we don't get cell center location until it's built, right?
No, you do.
We can ask for
Yeah.
cell center locations, yeah.
Yeah, you can get cell centers as it's being built. That's about it.
Okay, at the finest actual level.
You get cell centers, cell widths. Yeah, you get cell centers and cell widths as it's being built.
At the finest actual level, or
whatever level that cell is at.
Before you finalize. Okay, I see. So if I pass in a point, it will break down right away, and then I can ask him the cell centers right away. Is that what you're saying?
So if you build it from a function, so like the mesh's refine function.
Yeah, like not insert cell.
Instead of insert cell, right. So if you just use this refine function, so you can define a Python function.
Okay.
That would, and then pass it a function that operates on a cell, which is how it had worked previously.
Yeah, if you could provide an example, Joe, that would be perfect then.
Yeah.
So yeah, I guess we could do that for the surface as well, right? Just pass some sort of a inverse distance.
Yeah, so that's how I had done it a little bit with one of my examples that I was working with for the for my field camp students, which I still need to get up there. But the idea is that you just create an interpolation object, and then you can pass that to the mesh, like as a refine type thing, and then just measure, okay, how far away from it is the surface, and then refine based off of that level. Because you get, like I said, you get the cell center, so you can figure out its like the height of topography at that center location.
Yeah, no, that makes a lot of sense. Hey, Lindsay, we get a lot of feedback. Can you turn the volume down a little bit?
Can somebody turn the volume down just a touch? The other thing with that, Dom, too, if we go about it function-based, as Joe was saying, then it's easily, we easily get the case where you want to refine a box or refine around some complex target. So even if you had like the TKC surfaces, for example, we could then just define distance from like those surfaces as a function, and then have that be how the mesh is built.
Okay. Yeah. So if you guys can just provide an example, it'll take less time, I'm sure.
Yeah.
The thing that I wanted to talk to you about, Joe, is oh man, feedback is intense.
I'll mute on our end.
Okay, sounds good. Is to be able to plot to add. I basically just right now copied your entire plotting function and just added the part to be able to have vectors in it, like to have this quiver option.
Mm-hmm.
So we can have vectors in the model, right? I'm not gonna rerun this, but I think I've showed it in the.
Yeah, I've seen it before.
Yeah, you've seen it, right? Yeah, this guy.
Basically, in that function, there's a lot of logic to do a slice through it.
Exactly. Once we have the cell center location on that slice, then it's just instead of a single scalar model, it's just a 3-component.
Yeah. So have you looked at how they do it for the tensor mesh, like how it's plotted there?
Sorry, what the tensor mesh has stream plots, but do we have just straight up quiver? I'm not too sure.
No, so it's just they use the stream plot.
Yeah, and stream plots is good, but not for all problems. Sometimes it goes really crazy. It's kind of nice to just be able to ask for the actual vectors.
Mm-hmm.
If we have the option, that would be sweet. Yeah, you saw that, right? Yeah. So
yeah.
Dom, one
so I guess
thing. Oh, go ahead, Joe.
I guess my question is, what do you want it to look like?
I think just the quiver function is fine. It just shows the arrows, right? It just shows the arrow head. Yeah. And you can have like a few switches to be able to scale the width of it. Color, maybe have the option for the color. Yeah.
Yeah, that should be fine. I mean, it's just a small little addition if you want to put it onto the. Ideally, what I'm imagining is that we just have a unified 2D plot thing.
With for tensor and tree, you mean?
Not for tensor and tree, but just for the quad trees. So the quad tree and octree. So basically, what the octree function here is doing is it does a slice and builds a quad tree from a slice of the octree. So then, if we just have a unified way to plot vectors on the quad tree, it's a little bit. We can just work on that part.
Yeah.
And then just pass all the options through. Kind of, and I believe you guys do something similar to this with the tensor mesh, where there's just a unified 2D plotting.
Yeah, that's correct. That's correct. So we do, we build a 2D mesh based on whatever slice you're going to look at. One quick thing with the stream plots, what we actually do, because stream plots you can't do on a non-uniform mesh right now. That's a limitation of Matplotlib. And so there's a lot of sort of logic, I guess, in the stream plotting, so that the first thing that we actually do is interpolate to the finest cell refinement and then build the stream plot from that, which works reasonably well. What you have to be careful with, though, is if you have like very disparate scales, it can take a really long time to do that interpolation. And so there's also some parameters in there so that you can basically define a bounding box and say that I actually only want streams from like -100 to 100, even though my mesh extends out kilometers, so that it only interpolates in that region. So if that's something that we want for the octree, there's a few things that we can pull from that we learned on the tensor mesh side of things.
Mm-hmm. Basically, I would go about it in the same sort of manner. I mean, I don't think we need to build a interpolation matrix or do any of the fancy other stuff for this, because it's just mostly a one-time off plotting thing. So you could probably just get away with using a grid data function from SciPy.
Yeah, and the interpolation for octree is probably gonna get pretty intense, right? It could get intense, I'm guessing, if you're putting everything on a smaller cell.
No, it wouldn't look how you would expect it to look. Like, it wouldn't look smooth. There would be discontinuities at cell sizes or for cells because of the way that cell-centered interpolation works.
Okay. Yeah. No, totally. If you're in one of the big cells or not, you would see it. Yeah. So how do you want to proceed, Joe? You just want to move this elsewhere? Like, there's no point at having that function right now. It's just inside the example. I plugged this guy in, right? But this is basically just a first pitch at what we would like to have.
Right.
Yeah. I can leave it as just I can leave it inside the example just like that for now. Also.
Yeah, I would leave it in there for now. Like I said, it'd be better just have a unified 2D plotting thing on the tree meshes.
And how would you do? You would just detect if the model is a single vector or a 2D array. Is that how you do it?
I would do it the same way that it's done in the tensor mesh views, just to keep the
syntax the same. Yeah.
Syntax the same. Yeah.
Sounds about good. Yeah, that's it for. Oops, not that. This guy. Yeah, that's it from me. So, guys, put your comments. I think the function is probably the best way to go, right? For the refinement.
Mm-hmm.
If you give me an example, I'll review it, because we probably we didn't need all this stuff to like create clouds around it if it's just a function, I'm guessing.
Yeah, you don't.
Yeah. So your example would need to be for like a multiple points, right? Like a list of points or an array of points. We just pass a handle plus a cloud of points. Yep.
Yeah, I'm trying to think what would be the best way to do that. So, I mean, you don't want to have to search through a bunch of list of points every time you're calling the function.
That's why the cron was kind of like a fast way to do it, because that's really fast to do.
So Joe, you did use that quadtree example for DC, and can you share that example? Because I think there probably like how it might be nice to how you did it.
I might actually have it on here. Hold on. If not, I'll pull it really quick.
Well, while he's pulling it up, Dom, that looks good. I'll take a look at the PR, and maybe if Joe, if you have some time, if you could too, and we can figure out where things should live, because I do think a lot of what's been developed should actually be in discretized. And so, yeah, we can find a sensible place for it all.
Yeah.
Okay, I can pull it up, but I think I'm going to have to go offline for a second, because I got a VPN into the school's network and pull it off the computer there.
We'll see you again in a minute.
Okay.
While Joe is gone, I was talking. Thibault, is Thibault there?
Yeah.
Right. So we're talking about, because there's a bunch of stuff in there that is actually not really related to the tree mesh. For potential fields, I was updating a few things on the side, so we could probably just break that guy and merge the changes to your PF update PR, right?
Yeah, probably. Yeah, it's been sitting there for a while now. It's not.
Yeah.
There is nothing major, so hopefully that will be easy to bring it together.
Is that one that like is basically ready to go?
Like mine is actually pretty ready to go. Like it passed almost all the tests. Like coverage increase, quality is good. The only test it's not passing is that. Like I increased the general coverage, but the new line I've covered at like 70% instead of 72. And that's it. So
that's fine. Yeah, I mean, so if it's ready to go, then we can do a final PR review and try and get that in.
Yeah, it's also a solution. And then I can, if you want, I can be a reviewer on your PR done for the PF.
Yeah, because it looks pretty finished, right?
Yeah, it is.
Okay, I'll re-look at it because it's been a while, and hopefully it's good to go. Joe's back?
Yeah, I'm just still pulling everything off of the. Almost done. I had it all stored on the computer at school, so I had to copy it.
While Joe's pulling that up, are there any other things that we want to make sure we chat about today? No other items?
Yes.
No problem.
Yeah, one message I want to relay to, I guess, Dom and Doug. So, Dom, I met with Doug yesterday, and he was thinking about doing a GIF tools related meeting on Wednesday. I don't know when you're back.
No, I'm back Thursday. I mean, I'm flying back Wednesday night.
So we can have a meeting on Thursday?
Yes.
Perfect.
What do we want to talk about?
Oh, just kind of regroup, get updated where we are, and Yeah, reprioritize.
Okay.
Okay.
Okay, looks like I've found it. Just found a similar thing.
It looks familiar.
Okay, basically what happened was we kind of just built it off the DEC inversion example on their forum. Loaded in all their data. The idea is that it was a Renner, they were doing a Renner array. So I had to do a few little changes there to allow for like plotting of the pseudo section because it wouldn't quite work correctly. Basically, it just masquerades the Wenner array as a dipole-dipole array because that's basically what it is, except for how you plot the pseudo section. Anyway, so I've got the locations of all of the electrodes, the topography of the survey. And so this is where I'm creating the tree mesh. So I just have, I actually could change this right now, but I give it an initial x0 location, hx, hy, determine the levels, which now I should be doing it like this. So before the way, so I kind of have kept it the way it was before. There's two things. There's max level, and then right now, so there's mesh dot max level, max level. They do a little bit different things. So max level is just the max possible level of this tree mesh, and max level would only be the max used level of the tree mesh. Because this is
sorry, the max what level?
Used level.
Oh, okay, I see.
Basically, this just accesses the C tree, like the C implementation of the tree, to determine the max possible level. It's a little bit better and more robust to use this if you're building the functions, because there's a lot of logic that goes in determining what the level is, especially when there's differing numbers of cells in each dimension.
Mm-hmm.
Because it's not just as simple as, oh, it's the number of cells in this dimension power, but or 2 to the power, whatever. So anyway, I've defined a function here that works on the cell. From it, I can get the cell center, so I get the X and Z locations. There was just a little bit of logic here to see if it was outside like the bounds that I wanted it to be. And if it was outside the bounds of the topography. And then just kind of a fast exit. And then I just use my interpolation function on the X location and figure out what the top of the what the topography would be at that X location, and then compare the value of the mesh or the cell's Z location to the topography. And this was like a specifically defined function for this example, but you could also do things like get the cell widths. I think you can access that. Yeah, you can get the cell widths. The idea is that it creates a Python-like cell object. So Python cell object from the tree's C cell that you can use to access a bunch of the information on it. As it's being built, you get access to the center of the cells and the widths of the cells. And I think you could get access to the nodes of the cell as well. Yeah. Where the cell widths and the cell centers. So you could discretize or define based on the cell centers inside this function. It doesn't take too long to build the function or build this tree mesh, but it's only an octria example anyway. So if you can see, it's kind of hard to get this exactly.
To change other functions?
Say it again.
Joe, did you have to change other functions? In the I/O, for instance, like, or in the survey class?
I had to add a little bit to deter like this surface, this drape topo.
Right.
It had to get modified a little bit, and I think I pushed those changes to the tree mesh branch on SimPEG.
Okay. Cool. I see.
That's the only thing I really had to change as far as the tree mesh handling in 2D. Can't quite see it, so.
Oh, nice. Huh.
Joe, can I ask a question?
Yeah, sure.
So let's say you call that function, and then it's going to cycle through all the cells, right? And it's going to figure out, in your case, if you're above a certain elevation, break it to a level. Is that right?
So it cycles through the cells as they're being built.
So the order is important.
The order of the cells, you mean?
Yeah. So like, let's say you pass the first point, it will break it. It will find the level of that one and its neighbors, and then you'll be able to see what the next cell is.
So basically it gets called on each cell as it's created. So the first thing it does is the first level of the cell is the entire mesh, right?
Yeah.
So it calls that function on that cell of the whole mesh. And then it determines if it should break up the mesh. Well, obviously, yes, we want it to be broken up. And then it calls that function again on each of its children cells.
I see. And it keeps doing this until it's done. Yeah.
Right. Until everything is done refining.
Gotcha. But it doesn't go down all the children of all the cells. If one of the cell is like only the first level of tree, will it visit those children as well?
No, because it'll say that it doesn't need to be split. So it'll just, that recursion will end there.
That's great. Okay.
So it calls it like, so in this example, it would have called it on like all of these cells, right?
Once, yeah.
Once it'll get it, it would have determined that it wasn't going to be broken, so it wouldn't have called it on any of its children, which are not there, but it did call it on every parent on the way down.
Yeah. I get it.
And the same sort of thing here. So as it gets further and further in,
and Lindsay, when you were talking about passing a surface function, we're talking about like a Delaunay triangulation type of thing, or?
Yeah, I mean, so seeing like what Joe did up here.
So
Joe,
here,
yeah, go for it.
yeah, so this is where I'm creating an interpolation function using SciPy's interp1d.
And this returns a function.
It returns a function that is that just evaluates
Z
from X. Yeah.
And what's nice about that too is then you can choose, like, if your problem warrants a more robust interpolation, then you can just plug that in. And if not, then like using some of the standard SciPy interp1d, interp2d is fine. So like that can be quite flexible.
So we could do a distance from or something, yeah. And then if it's points, if it's scattered, then it's considered points. Otherwise, it's a surface. It's the line. Yeah.
And what you could ideally, I guess, what you could do with a distance to a bunch of points, a point cloud. I would honestly, I'd construct a KD tree from SciPy, and then use it to find the nearest point to the cell, because that's pretty quick. And then you could just check how far it is away from its nearest point.
Do you guys like the? I personally think more in terms of like how many octree cells. Maybe just because we're used to how UBC is working, but instead of a distance, it's more like I want 2 cells, 3 cells. What do you guys prefer? Should we work in distance or number of cells?
I mean, you could convert between the two.
Just have a switch.
Yeah. So, I mean, you could just have a switch, like, okay, if it's 2 cells distance or 3 cells distance, I want whatever that, you know, have a measure of that distance based off of those cells. And if it's whatever 3 cells worth of distance away, then you don't refine it as much.
Yeah, so we could have like a unit variable, I guess, if it's in meters or if it's in cells, and then we do the conversion internally. Yeah, I like that.
Yeah, I think sort of by default, though, working in distances is a bit more natural. I mean, we're used to working with cells because that's just the codes that we've been exposed to. But I think that, like, I don't know, I would suspect that most users working with just distances and like I need, you know, these 10 meters to be reasonably well refined might be a bit more intuitive. I don't know if you guys have opinions on that.
Yeah, we work, like we do something that's cell related, but it's just kind of like a natural thing to convert it to distance if you want, like, they kind of just interchange.
Yeah, that's fair.
I just gave you the option. It's easy.
Yeah.
Nice. Cool.
So you're doing a projection topography to your mesh?
So this moved all the electron points to the top of those hills.
Nice.
So you can just kind of see. It gets a little odd as you get farther away.
I think it's far enough.
So
that's where you could send one for your survey and one for your topography, right? You call it twice.
Yeah. Right.
Okay.
Yeah, this is kind of how you would use cell function. So if in 3D, you could cell center that way. It's actually a NumPy array. It's back to the NumPy array. I would go about like a lot of those things. There's a point for that insert cells, like insert cells at points, which is good. Like if you just, okay, I want to make sure that everything's refined around my observation points at this level. Or it's useful, but I feel like you can get a lot more powerful refined things, just designing a proper function to pass to it.
Yeah. Joe, do you think that you can generalize that function that could work, let's say, most of the 2D DC survey? Is that like fairly simple, do you think?
Probably, yeah. You just.
Yeah, I think that might be nice.
Yeah, just base it off of the like cell or the distance between the electrodes and maybe how wide your survey is, and maximum offset location.
Yeah, exactly. That's what I have in the IO, like just a rule of thumb. Use rule of thumb, like how many cells you want between electrodes, and then how you want to discretize, like using maximum separation, for instance. Like, yeah, that would be really nice to have that function. I think based upon that, I could try using that example.
Right. It should. I mean, it's pretty simple. I feel like it'd be pretty simple to just extend that to this kind of thing. Like, oh, I want them to, based off of the maximum separation between things, I'm going to discretize it as a function of it going down to that level.
Yes, and I think that's actually problem dependent. Having kind of like different functions for each problem will be actually useful to make our code actually useful, I think. Anyway, so that looks actually good. That seems like a good. Can you share that somehow?
Yeah, I've been meaning to put it up there.
Okay.
It looks, the results look weird, but
inversion doesn't look good.
it fits the data.
Sure, no problem. Okay.
What did I do?
I'm looking for a function to find a distance from a triangulated thing, you know? I don't know if there's one. Like Delany has a plane distance, but I'm not sure what it does.
So you're looking for distance from a point, like a cloud of points?
Well, no, like for instance, your example right now, you hard-coded that if you're like that far from the vertically up or down, we kind of need to generalize that to 3D. If you have like a triangulated surface.
Right. So I mean, the grid data basically could do that, or a similar thing, like the nearest the linear ND interpolator, right? That returns a function.
Nearest to what?
Not sure. That function is just basically linear interpolator, but Joe's.
Yeah. This
so we don't have to consider them.
So you could give it a bunch like your topography points and the values, right? And when your ND interpolator, it returns a function that you can use to call.
Right.
Yeah, no, I was thinking the other way, to triangulate first and then do a distance to surface, but you guys are just thinking in terms of nearest to the cloud. Yeah, no, I get it.
If you want to do like nearest to the cloud type of thing, and discretize based off of like how far away it is to like the nearest point.
Yeah, but I'm thinking because we want to do like a breakdown over distances, right? If you're 100 meters away, second level, third level, that kind of stuff. So it's not just like to find the closest ones. That's one thing, but we want to be able to figure out distances from a surface.
Right. So you could determine like maybe determine the convex hull.
Yeah, those functions they're heavy, man.
Yeah.
It's okay in 2D, but when you go to 3D, it's a hot.
Yeah, it's rough. Yeah, I know.
Anyway, we'll think about it.
Right. Good. That's very exciting. One comment about it's a different path. So we're actually like okay, this is a part of we're moving into a kind of scalable size of SimPEG code. I think another essential element, like if you're moving it that way, it's actually changing the field object. It just makes it really slow. It's actually nice and flexible, so I think there's some value. But if you actually want to run like a scalable algorithm in code, we definitely need to work on the field object. And I'm not 100% sure at the moment what is the best way. But I think even just using a simple NumPy array could improve the efficiency a lot, I think. So that's probably a good starting point, but it's a kind of trade-off, okay, how much flexibility we still want there. I think the current field object has maximum flexibility, I guess. We probably need to trade off a little bit. Yeah, so I'm not 100% sure, but we need some thoughts, I guess, especially for a lot of like PD solvers, EM problems or DC problems. So I think if that's the pathway, I think that's the bottleneck now. One bottleneck.
Yeah, there's a lot of things to rethink through that, and I also think that when we go through there, we should think about the API to the fields object, because it is like, it's an interesting idea, but it's also super strange and it's hard to figure out, like, unless you know that it's sort of this smart dictionary, like why are you indexing it like an array, but you're passing the string, and like, that's strange. So I think that having methods on, like, have your fields object, and then we can have basically like electric field. And then you call that with a set of sources and receivers. I think it's a lot more intuitive. So I think those things can go hand in hand.
Yes.
But that's a major structural change.
I think with that, I think there's a couple of things, right? Source and receiver class as well. I think it's awesome, but in a certain level, I think it's trade-off always, like efficiency and how you want to deal with that.
Yeah.
So I mean, that's a part of our trajectory. I think we probably need to modify a bit and improve the kind of efficiency thing. Well, we're not going to do it right now, but I think those are the items.
Yeah, absolutely. Well, I mean, if that's something that you want to dive into and even diagnose where the issues are and capture that in an issue on SimPEG, like, so knowing, okay, we've isolated the fact that the fields object is a bottleneck. I suspect that a lot of that is just the way that we are querying. And so if you have some examples that show that, that would be really
helpful. I
helpful.
did make some issues before.
Okay.
I think there is an issue in SimPEG, like slow field objects.
Okay. Well, maybe if you don't mind, just send it around on Slack again, and we can get people just thinking about it, and we'll keep it on the radar.
Right. Yeah, okay.
So Sag, before we quit, man, Anglo ran the 1D frequency on their data set, and it ran really smoothly. Really happy with the result. He would like to be able to add susceptibility to the inversion. Can we do this?
It needed a bit of work, but we could.
Okay. Yeah. That'll be good. And then we need to finish all the connections, right, to be able to have half space, best fitting half space. There's a few other ones that we need to finish.
What do you mean the half space?
To be able to start the inversion with best fitting half space. You know, do the.
Oh, I see. Yeah, I'm not sure that's a good way to go. So I don't actually see the value there, Dan.
Okay.
Yeah, well,
it's just to create a parallel with what they already have. But if you're saying let's not go there.
Right, but I think what we could do though, I think the current best fitting half space for each sounding, right? I think that way I don't really think there's a value, but I think like we could actually fit the full data set with the best fitting half space, like the full models, full data set. And I don't know, that's probably valuable, but I think doing each sounding for best fitting half space, I'm not sure there's value.
And Joel, okay, that's good. That's glad to hear this. He was proposing that instead of a best fitting half space globally, if we could do a best fitting 1D, so we can get a layered starting model, if that could help.
I'm not sure that I'm getting it.
So instead of a single best fitting half space, a single best fitting layered space for all of your soundings. So it'd be like a surjection map, basically, is you're taking your 1D layered earth and you're going to apply that to all of your soundings. So you're inverting for the same layered earth from every data.
So, but for a single conductivity, right? Is that
no, it's to deal with the case. Let's say you have like a tier layer and you have a background, and you would like all your stations to start with that layered earth, so that at least they're all starting at that same place, not the half space.
Oh, I see. And then that's what you're just setting, is that right?
That's what you would like to see, because in many cases you're just looking for one anomaly, but most of the area is kind of the same geology. It's like a till layer with a background, and currently all the stations are kind of starting at different places. Mm-hmm. So yeah.
But what's well, you can already do it, right? Like you can just set it from a layered earth initial model.
Yeah, but we need to build it. Like you could invert for it.
Oh, I see. Okay, I think for the SimPEG code, there's no problem. I think but you just need to have a setup, I guess.
The equivalent for UBC would be to have one sounding and throw all your transmitter receivers in that sounding. It will invert for a single model that fits best all. That would be the idea.
Oh, I see. Invert for a single layered earth. I see. Gotcha. I think there's no problem with that.
We can add the option. Yeah.
Okay, I see. Gotcha. Okay. Yeah.
And just one comment there. You'd have to be careful about all of the transmitters being at the same height above the earth.
Right. Yes. So yeah, the SimPEG code has a functionality to invert for height. I think we could put that in. Yeah, it works for just for single sounding, but I think I need some work if you want that for that laterally constrained inversion.
Otherwise, he was really happy with the result. Loved the speed up. He had like a computer with 20 processors, so he was ripping.
Perfect.
Yeah.
It's working.
That's it for me.
Sounds good. Yeah, we can talk about the details later.
Sounds good. Anything else from anybody else?
I'm working on spectral IP inversion. So actually, I'm working on a paper, and so I was working on the kind of repetitive waveform. So we usually assume like a step off, for instance, which is not quite the case. And then also we have a lot of different parsers, and we're stacking it. So I'm considering that into spectral IP inversion. So yeah, I think it's a part of a research topic. I think it's done. So I'm finalizing the paper, and I'll push probably merge that my branch into master pretty soon.
Nice.
I'll probably show you guys later once I'm ready.
That'd be great. Okay, well, thanks everyone. We will see you next week.
Thanks, guys.